Hey, Math 7195. Here we are in unit number 8. We're continuing on with inference. We're doing so with two parameters now instead of one. So basically we'll be comparing two populations. So we might compare the mean of two populations. We might compare the proportion of two populations. We can also compare the standard deviation of two populations. And we can do other things as well. But let's hit on proportions and means today. We'll have two different cases for the means, the dependent sample case and the independent sample case. So let's just dive right in here. With this hypothesis testing, now that we've done several, it's much easier to introduce new ones. Basically, I give you a new test statistic and I tell you what the conditions are to use that test statistic, and away you go. It's the same 8 steps that we've been doing. So if we're going to do the hypothesis test where we're comparing two population proportions, that's, proportion 1 versus proportion 2. We'll need to check a few things. Our samples will need to be independent, and we'll have to make sure our sample sizes are large enough, just like we did in the single proportion case. Now we have two groups. So we'll have N1 is the sample size of the first population, and P1 is the proportion of successes in that group. Our magic number is still 5, so we need these products to be greater than or equal to 5. We have to make sure it works for sample 1 and for sample 2, so that's why you'll see the additional conditions here. You'll also notice that I'm using P instead of pi here, because we often, when you're talking about two proportions, you don't make a claim about what the two proportions are. You make your claim based on how you're comparing them. Like your claim might be the proportion in group 1 is higher than the proportion in group 2. If that's the case, you don't have an actual value to substitute in for pi. So that's why we have to use P in the test here. Just like we did when we had confidence intervals, we did the same thing. When we're talking about comparing two proportions, there's basically two versions of the test. I've almost alluded to it already. The null hypothesis is usually that there's no difference between the two groups. The proportion of the first group minus the proportion of the second group equals 0, means that there's no difference. Or sometimes we'll have that be less than or equal to 0 or greater than or equal to 0. As long as it has the ability to equal 0, then we will use this version of our test statistic. When the null hypothesis is that the two proportions are essentially equal, that means that the two groups are essentially equal, and we can pool all of our data together and have this thing called a pooled sample proportion. Basically combine your successes from the two groups and combine your sample sizes of the two groups. Other times we will have the potential where maybe you'll say that you know how much larger one group is than the other. Or maybe I'll say the proportion of men that pass this course is 10% lower than the proportion of women that pass this course. Well, now my null hypothesis would be some value other than 0. And then I can't pool my data together because I'm saying that there is a difference between the two groups, and then my formula changes a bit. Notice we're still using z-scores. As long as sample size is large enough in proportions, we can use a normal distribution. We can set up our confidence intervals using the standard error formula too, where E is just this piece of the formula. Again, same conditions apply. We'll just do a bunch of examples now, and we'll see how this all works out. These are a little more, computationally slightly more intensive, but not too bad. Here's a little example. I once was hooked on a game called Guitar Hero, and when Guitar Hero 3 came out, it seemed a lot easier than Guitar Hero 2. So then I created this question based off of that. A computer game magazine claims that Guitar Hero 3 is easier than Guitar Hero 2. So they conducted a test, and they found some people that had never played Guitar Hero of any type before, and then they assigned them Guitar Hero 2 or Guitar Hero 3, and then they had them practice, essentially playing the game 1 hour a day for a month. And at the end of the month, they asked the people, have you completed the medium difficulty level? So assuming that they started on easy and worked their way up through the songs. This might not be the best way to, evaluate this, but let's, accept that that's a fair way of saying that one is easier than the other. If more people can complete Guitar Hero 3 on medium than Guitar Hero 2, then maybe Guitar Hero 3 is easier than Guitar Hero 2. So here are the results. 78 people were assigned to play Guitar Hero 3 for a month, and 63 of the 78 were able to get through the medium level in that time. Guitar Hero 2, 77 people were randomly assigned to play that game, and 43 were able to complete the medium level within the month. We want to do a formal hypothesis here. We'll test to see if, in fact, we believe that Guitar Hero 3 is easier than Guitar Hero 2. I'm going to call Guitar Hero 3 players group number 1, and I'm going to call Guitar Hero 2 players group number 2. Remember from our formula, we had all these subscripts, group 1 and group 2. So just so I don't get confused along the way, I want to make sure I label them so I don't. It's easy to start calling, if I called Guitar Hero 2 group 1, it might have been confusing, for example. Let's run through our steps here. Step 1 is write down the claim. They're claiming that Guitar Hero 3 is easier. And what does that mean according to, this experiment? That would mean that their proportion of Guitar Hero 3 players would be higher than the proportion of Guitar Hero 2 players. So the claim here is that the proportion of Guitar Hero 3 players is greater than the proportion of Guitar Hero 2. We like to write that as a difference. So, I'm already maybe confusing the issue by saying Guitar Hero 3 and Guitar Hero 2. So I'm going to label them group 1 and group 2. So I could rewrite this as Guitar Hero 3 minus Guitar Hero 2 proportions then is greater than 0. That's our claim. If I subtract the proportions, I would get something greater than 0 because pi 1 is assumed or hypothesized to be greater than Guitar Hero 2. Now we can set up our null and alternative hypotheses. And this case, the claim is the alternative hypothesis because it doesn't have any sort of equality. They didn't say it was greater than or equal to it. If they had said that, if we had an equal to sign here, then we would have put this as the null hypothesis. But because there's no equal sign, we'll have it as the alternative, and the null hypothesis will just be the opposite. Sometimes I just like to remind myself where the claim is. Is it HO or HA? Step 3. Set your significance level. They told us to do it at 0.01. The reason for that is 0.05 is too easy. We know that the critical value, we're so used to using our 1.96, it's good to shake it up a little bit. Step 4 is where you check your assumptions. For comparing two proportions, you have to check N1, P1, and see if it's greater than or equal to 5. For group 1, we tested 78, and 63 out of 78 were successful. This number is 63, which is certainly greater than or equal to 5. And then we have to check if N1, 1 minus P1, is also greater than or equal to 5. So 78 times 1 minus 63 over 78. And that will be 15, I guess, because it has to add up to 78. Also greater than or equal to 5. So we're feeling pretty good so far. This is a 1 here. We also have to check group 2, N2, P2. So we have 77 in that group and 43 out of 77, which is 43, which is greater than or equal to 5. And N2, Q2, or 1 minus P2, is 77 times 1 minus 43 77ths, which gives us 34. Also greater than or equal to 5. If any of these things fail, then we could quit and say we don't have enough data. We shouldn't perform this test. Maybe there's another test available for when this happens. But in this course, we don't know it. So that'd be a great final exam question if you could just quit at this point. It'd be brave to say it. Say, I quit. In this case, it was okay. All this tells us is that our sample size is large enough that we get to use the Z distribution. And then we can move on to step 5, which is where we write down our test statistic. For this one, it's P1 minus P2 minus pi1 minus pi2 all over. And then you have some P bar, 1 minus P bar, 1 over N sub 1 plus 1 over N sub 2. And there's some square rootage in the denominator. Notice I used the P bar formula for this one because my null hypothesis had the number 0 here. If it had said proportion group 1 was 10% easier than group 2, then I would have 10% here and here, and then I would use the other formula for Z. Remember, if we go back, we had two options here. It's almost always this one. Notice ours wasn't exactly equal. It was one of the greater than or less than or equal to options. But because our null hypothesis is that we're basically assuming the two groups are equal, which allows us to pool the data together. So our probability of successfully completing medium can be grouped together as, well, 63 from group 1 completed Guitar Hero, and 43 from group 2 completed Guitar Hero, and we had a total of 78 plus 77 people. That's 106 over 155. And now we can just substitute our values into the equation to figure out what the z-score is. P1 was 63 over 78. P2 was 43 over 77. The differences in the pi's, the null hypothesis says, we're going with 0 there. And now our P bar is at 106 over 155. And we still have 78 in the first group and 77 in the second. Some people might be upset that I didn't have the same size sample for each group, but that's okay. I mean, because we're talking about proportions. You wouldn't really want to compare maybe two groups if one had a huge sample size and the other one had a small one. And that would probably show up in the test would probably fail when you're checking your assumptions if you had one that had a small sample size. Calculating this out, I get 3.34, which is a rather unusual Z-score. But remember, this might be a one-tailed test, and then maybe that isn't that strange. It depends on which side it's on. But it is a kind of a weird Z-score. Step 6, we had two methods. We could do this using p-values, or we could do it traditionally. Take our pick. How about we do p-value today? And let's see if it's left, right, or two-tailed. I got to go back and look at my HA points the way. We would accept HA over HO only for large values. So it's a right-tailed test. So we take our Z distribution and we plot this 3.34 on it. And then we find the area to the right of it. It's probably not even in my Z table. Like that 3.34 is starting to be on the fringe of that thing. Let's take a look. Off to our Z table. And our table only goes up to 3. And it stops at 0.9990. That's the area to the left, remember. The table goes up to 3.09. And this area is 0.9990. So the area up here is 0.0010. So for our value, 3.34, I don't know what it is, but it's got to be smaller than this. So we can go back to our hypothesis test here. I can't get the p-value exactly from the table, but I can say it's certainly smaller than the smallest thing that's in there. And then we can do step 7. Basically, our result is unusual if we assume the null hypothesis is true. Therefore, we're going to reject the null hypothesis. Our p-value is smaller than alpha, so we reject the null hypothesis. And then we can do step 8 and come up with our conclusion. In this case, we're rejecting the null hypothesis, which means we're actually supporting the claim, because the claim is the alternative. And we get to word this strongly because we rejected. Rejecting the null hypothesis gives us a stronger conclusion because we can quantify the probability of our error. We know the probability that we messed up is our alpha, and in this case we'd set alpha to be 1%. So, final conclusion, we're supporting the claim. There is sufficient sample evidence. at alpha equals 0.01 to support the claim that Guitar Hero 3 is easier than Guitar Hero 2, at least by this testing method. You know, maybe the whole test itself isn't fair. The way that we decided to define what easier meant. But under these conditions, Guitar Hero 3 is easier than Guitar Hero 2. It might not have been fair. Maybe the songs were shorter in Guitar Hero 3, which meant they were only allowed to play 1 hour a day. And if the songs are shorter, it would be easier to progress through the game. Or, you know, there are little things in it that might have made it unfair that, you know, we would have to check. If you're an Excel person, I guess we could have calculated this p-value exactly, right? We could have said p-value is, we use that norm.dist, but because we want the area to the right, and in Excel, it gives you the area to the left. So we'll have to do 1 minus norm.s.dist. And then we input our 3.34, and we tell it that, yes, it is a cumulative value. In fact, I did this in advance so you could have a template if you want to do these in Excel. I cut and pasted the question in here, and I wrote it up exactly the way we wrote it up. And you see that we get the same values. I calculated P bar, I calculated the Z-score. We had 3.34, so it matched. And then I did the test statistic. Sorry, this is a traditional critical value. I did both methods, basically. I did the traditional method and the p-value method. The traditional method was I found a critical value on the right side, which you can see here is norm.s.inv, and I had to put 99% in because alpha was 1%. The Excel works to the left instead of to the right, so you have to be careful that way. So if you're a traditional person, you'd be comparing 2.3 and 3.3, and you'd say 3.33 is way bigger than 2.3, and by bigger I mean to the right of it because it's a right-tailed test, and then you'd reject. If you're a p-value person, here's the formula we just written down, 1.norm.s.dist, and I went with this 3.34. And you can see the p-value is quite a bit smaller than we thought it was even. We said it was smaller than 0.0010, and it's actually 0.0004. Either way, we're going to reject the null hypothesis, and we get our conclusion. So, yeah, in Excel, it's okay to do this. It's a bit of a hassle to type the Greek letters and stuff to make it look pretty. In Excel, if I want a Greek letter, the way I do it, if I want pi, I type a P, and then I change the font. I just change the font to symbol. And that's how I get my pies. If I want a subscript, I just typed the number, and it's not right yet, but after I have the number there, you can go and highlight it in the formula bar here, and then right-click on it and format cells, which seems weird since I'm only formatting, one little piece of it. And then there's an option for subscript and superscript. So that's how I made these things look pretty all along here. Basically, I typed it once and I copied and pasted them all and edited them as I went. Just so you know how to do that if you ever want to. You don't need to make it like that. that nice, I was lazy with p bar. A lot of times if I'm doing something like this, I would just write, pi 1 is minus pi 2 greater than 0 or whatever. And, it's good enough for me to remember it. But I just wanted to show you that in case you wanted to, ever do anything all in Excel like this. On your final exam, I typically have you write out your test even if you use Excel to help you. So for a question like we just did, your answer would look like we did it here. You'll write this whole thing out, and you'd use Excel to get the 3.34, and maybe you'd use Excel to get this p-value, which turned out to be 0.00043 if I recall. And then, so you're still going to show me that you can write these things out. And I think it's faster to write them than to try to type it and make it look pretty like this. Of course, now you have a template. If you ever need to do a hypothesis test comparing two proportions, you could start with this page and start editing the values, and you probably come up with a pretty nice looking hypothesis test. So there, that's comparing two proportions using a hypothesis test. We can compare two proportions making a confidence interval. I did the same example, construct a 95% confidence intervals for the differences in the proportions. So here's a case where, say you don't have any claim, then you construct a confidence interval. And again, you check your assumptions like we did, and then you just plug the things into the formula to get your interval. Calculate your error. If you're doing 95%, your z-score is 1.96. And you come up with a nice little interval. The actual proportion, the difference between the two proportions is somewhere between 10 and 39%. If somebody said that Guitar Hero 3 was 50% easier than Guitar Hero 2, you would reject that because 50% didn't fall in this range. But if somebody said, oh, I think Guitar Hero 3 is 30% easier, well, that falls in the interval, and you probably wouldn't disagree with them. So we can use these confidence intervals to evaluate claims as well. They just aren't as formal. And notice, I just blasted through that. Basically, those confidence intervals are, even hypothesis tests, it's basically just going through the formulas. Figure out which formula to use and go through them. We can move on to comparing two means. We just did two proportions. Now let's compare the mean of two groups. And we'll do the case where the two samples are independent of one another. So the subjects in one group have nothing to do with the subjects in the other group. So that's what I mean by independence. We'll make no assumption about the variances of the groups. If you do know something about the variances of the groups, you can actually tweak your test statistic. Actually, you tweak your degrees of freedom a bit. But let's just do a case where we're never going to know anything about our variances, and therefore we'll use the formulas given here. But in order to do a comparison of two means, we're going to do the case where we don't know what sigma is, which means we will use the t-distribution. And in order to use a t-distribution, we need either that the populations are normal to begin with, or we need to make sure our sample sizes are large enough, using the magic number of 30. But once we do that, we're on our way. We have a t-score for our test statistic, and we have our error formula for our confidence interval. The only other thing we need in order to do this test is to know the degrees of freedom. For this test, we have two groups. So we'll just take the smaller of the two. So we could maybe write it as, the degrees of freedom equals the min of n1 minus 1, n2 minus 1. Whichever one of those is smaller. This is a conservative way of handling the degrees of freedom. If we had additional information, like I know that the variation of group 1 is the same as the variation in group 2, then sometimes we tweak the formula for degrees of freedom. We can use a higher value, which is less spread out then. Diving into an example, you can see if we apply these formulas, we're going to test out a drug. We have two groups. Some people are going to get the drug, and some people are going to think that they're getting a drug. That will help eliminate that whole, those effects of, do you know if you're in a study or not? In this case, everyone knows that they're in the study, and they all think that they're getting some sort of treatment. So we're giving them this new cold medicine, and we're testing to see if it affects their blood pressure. Ideally, we don't want cold medicine to affect blood pressure, because then it's safer and we can, market it to more people. So we're going to check their systolic blood pressure and compare the two groups. So 50 people got the drug, and I tested their systolic blood pressure, and the mean turned out to be 203.4 millimeters of mercury. And I tested 100 people that were getting just a sugar pill or something, something that didn't actually do anything to blood pressure, and their mean systolic blood pressure was 189.4 millimeters of mercury. The units here, and the standard deviations are given too. So we don't have the raw data, we just have the summary stats. But we can go ahead and do the test. Let's see if there's a claim in here somewhere. So we read through this and we see that the head of research at the company claims that Dozanol does not affect blood pressure. So that is our claim here. Dozanol does not affect blood pressure. So that's our step one. We need to convert that claim into, our mathematical symbols here. Step one. In order to keep everything straight, I'm called the treatment group, group 1, and the control group, group 2. It doesn't matter. Just make sure you keep it straight all the way through. We're saying that the blood pressure would not be affected by Dozanol, so we're saying that the two groups should have the same blood pressure on average. So the mean of group 1 should equal the mean of group 2. That's the claim. Maybe I'll write claim there. mu1 equals mu2. That's a more convenient way to write it, but really, when we go to our formulas, we'll have to insert mu1 minus mu2, which equals 0. Just rearranging the algebra there. Step 2, set up your null and alternative hypotheses. This is the null hypothesis because it has an equal sign. And the alternative then is just the opposite, that the means are different. Step 3, set your significance level. They said the probability of a type 1 error here is 5%. Step 4, check our assumptions. Do we know anything about sigma? No. We only know about S. Do we know anything about the populations of the treatment group and the control group? It didn't say it anywhere, and we don't care because our sample sizes were large enough anyway. If these were under 30, then we would need the population to be normally distributed. But since our sample sizes are large, this allows us to just forge on and say that the differences in our sample means will follow a t-distribution with degrees of freedom equaling the smaller n1 or n2 minus 1. So degrees of freedom will be the min of 49 and 99, which is 49. Step 5, calculate your test statistic. Go back to your previous page, go look it up. It's x1 minus x bar 1 minus x bar 2 minus mu1 minus mu2 all over s1 squared over n1 plus s2 squared over n2. If we could assume that the two populations had equal variance, this formula changes a little bit. We can actually pool our s's together, kind of like we did when we had proportions. But let's not deal with that case, because this is a more general case. We're making no assumptions. Plug all our values in here. X bar 1 is 203. X bar 2 is 189. Mu1 minus mu2 is 0. S1 is 39.4. S2 is 39, and we know our n's. So 203.4 minus 189.4. I almost didn't write it. I almost got too lazy to write it. S1 is 39.4 squared over 50, and S2 was 39.0 squared over 100. You get a t-score of 2.06. I hate 2.06 because a t-score of 2 is, it's like having a z-score of 2. It's sort of kind of weird, but maybe not weird enough. And I can't really judge this thing without step 6. So this is a case where we really need to do the formal version because it's hard to evaluate this t-score. Step 6. Pick a method, any method. Let's do the p-value method. My favorite. Is this left, right, or two-tailed? Well, I need to go back up and look at my hypotheses. What would make me reject the null hypothesis? Well, I'd reject that if I had a difference that was way above 0 or way below 0. So it's a two-tailed test. Basically, HA says it could, as long as it's different from 0, reject. And by different meaning it could be above or it could be below. We're using the t-distribution. We have our value here, our test statistic of 2.06. And because it's two-tailed, we'll put negative 2.06 there too. And the p-value is the area to the right of positive 2.06 and the area to the left of negative 2.06. Our t-table doesn't have negatives in it, so let's look up positive 2.06. But we need to know what our degrees of freedom are, and we already decided what they were. The degrees of freedom will be 49 in this case, the smaller of 49 and 99. So row 49 of our positive t-table, looking for 2.06. Let's see if we can find that thing. Here's our t-table. We're looking in row 49. Oh no, we don't have a row 49. We have a row 50. That's pretty close. And we have a row 40. Remember what number we're looking for there. We're looking for 2.06. It's not in the table. It would be between these two if I had a degrees of freedom of 40. And it would be between these two. Oh no. Would it? Oh, this is kind of tricky. 2.06, I guess, is between these two. Actually, I had it wrong on the first row too. It'd be between these two. So even though I don't know what 49 degrees of freedom would be, the pattern would continue. So if it's between these two values at 40 and it's between these two values at 50, it must have been between these two for at row 49, which corresponds to probabilities of 1% and 2.5%. So the table's kind of rough there, but we did the best we could. Lost our page. Our p-value. This area here, we said it was between 0.01 and 0.025. We don't know exactly what it is. And this area down here, same thing, 0.01 up to 0.025. That didn't turn out that great. Let me try again. So my p-value is the total. It's basically, I'm summing those two things together. So I guess I could put it as a range. You know, it's between 0.02 and 0.05. And then we can do step 7. We're going to compare our p-value to our alpha. Our alpha was 5%. Our p-value is smaller than that. We don't even know what it is, but we know it's under 5%, which means this is a fairly unusual thing. So we will reject the null hypothesis and then write our conclusion. Our conclusion will be, I guess, let's look at what we had set up here. We rejected the null hypothesis, which was the claim. So we're rejecting the claim. And we can say this somewhat strongly because, again, our decision was to reject. So we will be able to say that we're rejecting this claim. There is sufficient sample evidence at alpha equals 0.05 anyway, to warrant rejection, or just to reject the claim that Dosanol has no effect on systolic blood pressure. mean systolic blood pressure. This is a terrible hypothesis test. I hate this test. The reason I hate it is that our p-value was such a, it was kind of in the gray area. Our p-value is smaller than alpha, so we rejected the null hypothesis. But what if we changed alpha? If we had initially in step 3 written alpha equals 0.01, which is a very common choice, our decision in step 7 would have been fail to reject the null hypothesis, and then we would have said, well, we can't reject the claim, which basically says we're agreeing with the claim. So when you end up with a situation like this, where your p-value is between 0.01 and 0.05, you probably cannot publish your results. You would need to gather some more data before you can really draw anything conclusive. If you're worried about our p-value, we could calculate that thing using Excel, t.dist.twotales, and then you plug in 2.06, and the degrees of freedom, and it'll give you the exact value, which in this case, I believe it turns out to be 0.04. .0448 actually. So pretty close to 0.05. Again, a bad p-value. I did this in Excel as well. So you can take a peek at this example. Again, I followed through the exact steps. I wish Excel had like a built-in hypothesis test where you could just, give it the data and it would give you the p-value. And it actually does if you have the data itself, like the raw scores. Like if I had the 50 values of group 1 and 100 values of group 2, then you can just enter that data and go to your data and then data analysis tool. We did descriptive statistics that way. There are hypothesis tests in here too. One of them is a t-test assuming unequal variances. That's the way we handled this. And it would just give us the p-value for the test. You just have to input the data, the data for group 1 and the data for group 2, and you tell it what your mean difference is, in this case 0, and it spits out a nice summary. But when you already have the data summarized, Excel can't do it. So again, I just typed it all up nice. Again, I have a typo in here though. When I did my traditional value, I called it a traditional test statistic, I guess because I cut and pasted it from the last one as I was setting up this template. This is a traditional critical value. So if you're you can see that if you're a traditionalist and you'd be comparing this T alpha over 2 to your test statistic of 2.05, and you see that 2.05 is slightly larger than 2.01, so you reject the null hypothesis, or you calculate the p-value. I put the formula in here for how to get the, this is basically reverse reading the t-table. So you have t-inv, and then for p-values you have t-dist. You can always check this out. I'll post this for you. And again, I put the same note here that this was a bad test because our p-value is so poor. And by poor, I mean so close to 0.05. So yeah, there we go with that. Make sure I hit save so I don't keep that typo around forever. We can move on. We have one more hypothesis test type for comparing two means. It's comparing means when we have dependent samples. I think I'll save that for I'll break this up and I'll put that in the next video. So you guys all take care and have a good day, and we'll pick that up in the next one.